who have joined the second day first session of the FDP on recent issues and challenges in AI and communication. Today, I have with us Professor Manoj Kumar, sir, from Delhi Technological Institute. Professor Manoj Kumar is a distinguished academician with extensive experience spanning over 3 decades in teaching, research, and administration. At present, he is professor and head of department in the Department of Computer Science and Engineering at Delhi Technological University. He holds BTech in Computer Science from NIT Calicut, MTech from IIT Delhi, and a PhD from DTU itself. His research interests includes data structures and algorithms, information security and cryptography, natural language processing, and machine learning. Professor Kumar has authored numerous publications in prestigious journals, conferences, and contributed significantly to projects involving NLP and database security. In addition to his academic accomplishments, he has served in various leadership roles with his dedication to knowledge dissemination and innovation. Professor Kumar is a mentor to many aspiring researchers and trusted guide in the field of computer science. So, without wasting any time, let's hear to what Professor Manoj Kumar has to offer. Over to you, sir.
Thank you. And let me start thing. My screen is visible.
Yes, sir.
Yeah, good morning, everyone. And my today's topic will be AI chip technology. We all are working in AI machine learning fields. Nowadays, I think all research work are in computer science are in field of AI and ML. And I hope everyone is familiar with AI ML techniques. Mostly in AI ML, we do some sort of training on large data, and then we try to predict something or infer something from for some new data. So learning and then prediction or inference is there. So this involves very large amount of training data, which we need to train. Usually we use deep learning or neural network for this. So that neural network technology is basically using large amount of data and to train the network and later on infer the result on new data. So definitely this complex and large volume task cannot be performed on normal CPUs. So normally nowadays some of you prefer GPU, but GPU was not designed for AI applications initially. This was designed for graphical applications like if you are processing images or videos. Images are basically we can say it's a stored in matrix form. So some sort of matrix operations are there. So those GPUs are suitable for matrix operations and image processing applications, but same matrix operations we use in ML also. So that's why if you are very expert in coding GPU, then you can utilize capability of GPU to solve your machine learning problems. So as I said, all AI tasks which we want to do is usually computationally expensive. The complexity of working, training deep learning models, processing large data set, and performing inference operations, they need uh, very smart hardware, okay, to perform this task. So suppose we use simple CPU on for our ML applications. The normal CPUs are basically programmable processors that can perform any task depending on the program loaded into memory. For AI application, it is used to process serial jobs and for system level control in the domain of AI. So what all calculation we want to do on do for our machine learning application, that will be done in serial. Suppose you want to multiply thousand elements with thousand elements like vector multiplication type thing. Your in matrix multiplication also that multiplication is there, like one row of one matrix will be multiplied with one column of another matrix. Means inputs are multiplied by weights and they are fed to one particular neuron, and then some of these will be taken and then we apply some activation function and we get the output. So this complete task will be performed serially if we are using a simple CPU. So these CPUs are not best suited for deep learning workload, but they can perform simple AI tasks, data processing or data pre-processing or controlling other hardware component, etc. So next comes concept of GPUs. So GPU are very good at performing tasks in parallel because they are having multiple ALUs or multiple cores. So each core can do one single calculation and multiple cores can work in parallel so that multiple multiplications can be performed in one step itself. So that capability can be utilized for training neural networks. This architecture will therefore be fit to perform many computations concurrently, and that will be well suited for enormous matrix computation, which is required in deep learning applications. So nowadays GPUs are used for most of the AI applications. We use it for training deep learning models and processing images and video processing also. And execution of complicated simulations also are done on GPUs. Most widely adopted kind of GPU among AI researchers is one enabled for CUDA and NVIDIA. Then comes the next generation of hardware, that is, we call it TPUs. So many of you might not have heard about this, but some of you might have heard about TensorFlow and by Google. So TPUs are custom developed hardware by Google for a specific purpose of accelerating AI workload. So they will help you in accelerating those training by in deep learning models. So they are optimized for tensor operations like vector operations, which are used in many AI models and form the core basis for deep learning. Use cases are TPU are widely applied in cloud services by Google for training and inference on deep learning models at large scale. They bring immense performance improvement over GPUs in some artificial intelligence workload. Then we have another category of hardware which can be used for AI, that is field programmable gate array, FPGAs. What FPGAs are basically, these are programmable devices where we can design a particular function by programming these FPGA components. So these are called normally flexible hardware used to implement the most suitable algorithm specific for a certain AI task in order to achieve a balanced view between performance and adaptability. So suppose you want to implement a particular ML algorithm for particular set of data, particular size of input, and particular size of output. We can program it in a FPGA chip. So we can make the circuit, we can program the circuit and use it forever. But this is having a flexibility that later on, if you want, you can reprogram it and tune it for another ML application of almost similar size. So FPGAs are used in AI real-time applications where low latency is required, means we want very fast results such as autonomous vehicles and high frequency trading systems, stock market, etc. Other category of hardware is ASICs, we call it application specific integrated circuit. This is similar to FPGA, but flexibility component is missing here. Means suppose you want to design a hardware for particular machine learning application, then this particular chip will be designed for a specific purpose, and that flexibility of reprogramming will not be there. So for a specific need, we design a particular IC. So this designing and fabrication of that particular chip for particular application will be very costly. So, but in AI field, if we are efficiently designing these chips, so they bring up maximum efficiency and performance to do what is required out of a certain task, but come at quite a higher cost in developing, and it will take time also because we'll have to go for fabrication and all. So ASICs find applications in scenario where AI task is well defined and fixed. Means that flexibility we don't want and doesn't require hardware flexibility. For example, large data centers or embedded AI systems where a task is fixed that on particular data we have to train the network and give the real data sizes is not changing, and always that hardware will be working for same task. Then for these AI hardwares, we need support of memory and storage also. So as AI workload is too high because we have to process very large amount of data, that is your training data. So too much RAM is required to store and hold the data during computation. So normal RAMs are will not be sufficient for these applications. So if you are having large scale data sets and models, fast storage solutions like NVM SSDs would be integral in data fetching and handling processes. These special kind of memories and storage are used in various AI applications. So these memory are having high memory capacity where we can store the training data, large training data, and these are having high complexity. Storage should be very fast so that we can access any element efficiently, and we can store all intermediate reals and data in that memory. Other than this, we need efficient networks also for AI applications, specifically if we are running our AI application in cloud or edge computing or for computing infrastructure, then high-speed network forms the backbone for effective communication of various nodes within a cluster or among edge devices or cloud server, which become critical for all distributed AI systems. So networking is one of the most fundamental dimensions of cloud-based AI platforms and distributed computing environment where data and computations are shared with others. So, so finally, I'll discuss all these hardware which are currently being used for AI and ML applications. But nowadays, research is going on AI chips. That is next generation compared to TPUs. So complex AI algorithms require massively parallel computation and specialized operations, which put increasing pressure on traditional processors such as CPUs and GPUs. Though versatile general purpose CPUs are not tailored to artificial intelligence computing need, the sequential processing nature of these chips, where they execute one task at a time, doesn't suit the parallel nature of AI computation. Because suppose you are computing this, you are training the neural network, and for particular layer, you are making the computation, then you should do it in parallel for all the nodes of a particular layer. So that parallelism is required in AI ML applications. Not even GPU, which are originally designed for graphics rendering, can adequately meet the demand for specific mathematical operations and memory access patterns that are common in workload related to AI. Because suppose we want to compute output of a particular neuron, then on that neuron input will be coming from all neurons of previous layer, and then weight will be associated with each input coming to this neuron. Then those inputs and weight vectors will be multiplied. So this is very special operation related to machine learning. So if you compare simple CPU and GPU, then CPU is having few complex cores, very means we can have 2-core machine or 4-core machine like this only. But GPU will be having hundreds of simple cores so that we can do parallel computations. Same task or a similar task can be performed in parallel. CPU focuses on doing one task as efficiently as possible, whereas GPU focuses on doing various tasks parallelly. CPU used for general purpose tasks only, whereas GPU used for graphics processing or matrix multiplication specifically. Then for if we go to tensor processing unit TPUs, this is well suited for our AI applications. Our AI application will be having this type of network where this deep learning layers are there. So I have shown a network here. So where many inputs are there and many three hidden layers are there. Each input is connected to next layer, and input will be connected to all the nodes of next layer. Then output will be generated with each input going to each neuron. Some associated weight will be there. So we are having set of weights, set of inputs for each layer. So these form the matrices. So large number of matrices will be there for every training data. Suppose we are having 1,000 training data, for every input will be having a set of matrices to be used in each layer computation. So process of running a trained neural network to classify data with labels or estimate some missing or future values is called inference. Normally we do inference for in a neural network or deep learning. For inference, each neuron in a neural network does the following computations. Multiply the input x with weight w, both will be the vector or matrices to represent the signal strength. Then add all these multiplication results, aggregate it, which will be a single value, which is called neuron's state. Then we apply activation function f, such as ReLU, sigmoid function, or 10H function to modulate the artificial neurons activity. Means this sigmoid function or activation function will be applied on the single value aggregated by adder and will generate a single output of that neuron. That output will be fed to next hidden layer or next layer of the deep learning model. So this is type of processing requirements of our AI applications, that matrix multiplications will be required, aggregators will be required, means so many data we have to add into a single value and then apply activation function. So if we do all these three tasks on a single chip itself, it will be a better. So TPUs are basically doing this. So Google had done one survey earlier, some 4 or 5 years back, in around 21. Then that how many multiplication operations would be needed in various like neural networks. So MLP 0 model, number of network layers are 5, number of weights maybe 20 million for a large data set. MLP1 is having 4 neural network layers and 5 million weights. And these two comprise of 61% of total ML applications running in the world. Then LSTM models, 0 model 1, they are having around 58 or 56 network layers, and the number of weights, if you count 52 millions or 34 millions, and around 29% of applications fall into this category, which are running on Google. Then CNN model 0, model 1, normally 16 or to 89 network layers and 8 million to 100 million weights are there. And roughly 5% applications are of this category. So you can see here volume data, volume weight here. 20 million, or we can say 5 million to 100 million weights will be there, which we'll have to deal again and again. These weights will be used for multiplication, addition, etc. Then weights will be updated. So temporarily we have to store these weights in somewhere in fast memory. We have to update the weights, reuse it again and again and again during the training of neural network. So now, so every single prediction requires many steps of multiplying processed input data by weight matrix and applying an activation function. So at every node, activation function will be applied, matrix multiplication will be done, the summation will be done. So in total, this is a very massive amount of computation required at each node. A first optimization, rather than executing all these mathematical operations with ordinary 32-bit or 16-bit floating point operations on CPUs or GPUs. Normally, what we do, if someone have programmed these deep learning applications in C or some languages, they know that all inputs and weights are represented as floating point number, 32-bit floating number or 16-bit floating point number. And you know, all these floating point multiplications are very costly in sense of time. You need a costly hardware to multiply two floating point numbers and generate the result. And in parallel, you want to do it, thousands of such units will be required to perform the multiplications in parallel. So we apply a technique called quantization that allows us to work with integer operation instead. So these floating point numbers will be replaced with 8-bit integer operations. Okay. So this enables us to reduce the total amount of memory required, like 32-bit earlier for each weight and input. Now we need only 8-bit for each input or weight. So obviously, if you are using integer instead of floating point numbers, later on we have to do normalization when we before computation of activation function. So this enables us to reduce the total amount of memory and computing resources required to make useful predictions with our neural network model. So this quantization work we can perform before actually starting our training work, so that memory requirement is largely reduced around by 1/4. Like I have given, see, neural network prediction often don't require these floating point calculation with 32-bit or 16-bit. So we are reducing it to 8-bit integers to calculate a neural network prediction and maintain the appropriate level of accuracy. So this 32-bit pattern, 32-bit numbers are now represented as 8-bit number, which is having some range 0 to maximum. So quantization is a powerful tool for reducing the cost of neural network prediction, and corresponding reduction in memory usage are important as well, especially for mobile and embedded deployments. So if we are reducing the size of memory requirement, we can deploy these applications in mobile and this handheld devices also. So when you apply quantization to interception, the popular image recognition model, it gets compressed from 91 MB to 23 MB, about 1/4 of the original size. So suppose in GPU, you are doing the quantization for image, your image size will be reduced to around 1/4 of the original size. Being able to use integer rather than floating point operations greatly reduces the hardware footprint and energy consumption of our CPU. So definitely 8-bit multiplication will be very simple. Very simple hardware will be there that will consume less energy, will take less time in computation. So normally this Google TPU that contains 65,536 8-bit integer multipliers. So you can see here, this is basically 256 cross 256 multiplier are used in this TPU. So you can do around 65,000 integer multiplication in parallel. The popular GPU used widely on the cloud environment contains a few thousands of 32-bit floating point multipliers. So GPU are still using floating point multipliers, and that are few thousands in numbers. So if you are using GPU, you can perform several thousand floating point multiplication in parallel. So if we are doing quantization, we are working with only 8-bit data, 8-bit input, 8-bit weights, and later on normalization process is done to reduce it to value between 0 and 1. that is normally done in classical deep learning models. So by doing this, we are speeding up by factor of 25 or more. Okay, number of multipliers are basically in the same pack or same chip. You can have more number of multipliers because now multipliers hardware is very simple compared to 40-point multiplier. So more number of multipliers you can accommodate in same chip. So compared to GPU, TPU, you are having 25 times more multiplier units. This is a typical architecture of TPU. So we are having here DDR RAM chips, some with some interface. The RAM chips will be storing your weight matrices. So those weight matrices will be coming into this matrix multiplier unit, and there will be a FIFO queue type thing because we know the current weight we are using, the next weight we know which set of weight will be the next one which will be used. So we can prepare a pipeline type thing in this unit, that is weight FIFO or weight fetcher. Then we are having a unified buffer, that is local activation storage, where all intermediate values, computed values will be stored. So this multiplier result will be stored there. Okay. So later on, summation will be done on those stored data, and finally activation function will be computed. So this matrix multiplier unit is having around 64 or 65,000 multiplier units, and then followed by accumulator unit, so that multiplication results can be summed together in parallel. Okay, and then finally activation function is applied, normalization is done to convert those values, and then store it in this unified buffer, or that is a local activation storage. So this TPU mainly contains matrix multiplier unit called MXUs. I just explained 65,000, more than 65,000 multiplier units are there. A unified buffer, that size is around 24 MB of static RAM, that work as a fast register, so that data can be easily accessed, easily stored, easily modified. And we are having activation unit, a hardware activation function. We don't need a processor here to compute activation function like sigmoid function. A hardware will be there that will be computing that function internally, and because of hardware, this function computation will be very fast. Now these TPUs are having some typical instructions, like some of the instructions I have explained here, like read host memory, that is reading data from memory, read weights, so read weights from memory, so weights will be fetched into prefetcher or FIFO queue. Then matrix multiply or convolve unit, all multipliers will be here. So multiply or convolve with data and weights and accumulate the result. So this multiplier unit will be doing this, multiplying two vectors and summing up all the results using accumulator. Then activate instruction will be there to apply activation functions, and usually we can have multiple units for different activation functions, and you can decide which activation function to use. Then write host memory, write result of this computation back to memory, so that that result can be used in next iteration of training. So this is a typical TPU multiplier unit, you can say. So this is 256 cross 256, 256 multipliers are there, and result of these multipliers are connected to adders. So to accumulate the data, because this result of multiplying two vectors, we have to sum and then generate the single value for a particular neuron. So those adders will be there, accumulators will be there, that will be performing summation in parallel. So here you can see the speed. TPU runs at 700 megahertz. So TPU can compute 65,536 multiplied by this amount, 700 millions. That comes around 46 into 10 raised to power 12, multiply and add operations, or 92 tera operations per second. So many operations per second are being performed by this multiplier and accumulate unit combined. Because this is in teraops, so we call it. We can say it's very, very fast compared to GPUs. So in short, the TPU design encapsulates the essence of neural network calculation and can be programmed for a wide variety of neural network models. To program it, we create a compiler and software stack that translates API calls from TensorFlow diagrams into TPU instructions. So normally we run a Google application that is on top of TensorFlow, and that is going to stream executor API, then user space drivers and kernel driver, and finally tensor processing unit is processing it. If we compare TPU and GPU, TPU is application specific integrated circuit, or ASIC we can say, where GPU is a specialized electronic circuit, a general purpose we can say graphics processing unit. TPUs have the capability to work faster as compared to GPUs while using fewer resources, whereas GPUs have the capability to break difficult problems into separate tasks and work them all right away. So like if you are having very large matrix multiplication in GPU, that large matrix multiplication will be broken into smaller matrix multiplication, and those multiplications will be done in parallel, and then result will be combined to give the final result of multiplication. A single cloud TPU chip includes two cores based on Google, which uses MXUs to speed up the programs through dense matrix calculation, whereas GPU includes hundreds to thousands of cores. See here, thousands of multiplying unit matrix multiplication units are there, whereas in GPU we have hundred to thousands of cores which are doing calculations in parallel. Okay. TP performs 4 trillion operations for each second by using simple 2 watt of power. If you compare the power, whereas GPU consumes up to 350 watt of power to do the same calculation. So compared to GPU, TPUs will be energy efficient in nature. So now next comes the concept of neural processing unit, NPU. This is the next generation of AI chips which enables AI applications to achieve new level of performance and fully utilize their capabilities through specialized hardware units and parallel computing. So if we compare the compare the different hardware requirements for artificial intelligence, in CPUs we are having versatility. Like CPU are general purpose and can handle wide variety of tasks beyond AI. Means they can perform normal operations also. Then we have sequential processing, good for sort of work that either cannot be done in parallel and has high single thread performance requirement. And this is very cheap, so this is affordable. But limitations are there. Parallel processing powers are not there. CPUs are less efficient compared to GPUs for tasks demanding parallelism, such as deep learning. And performance is also poor compared to other things like AI tasks, especially the training of big models run more slowly on CPU compared to GPU or TPU. So this is used only for general purpose computing and data pre-processing work of AI ML applications. GPU will achieve the parallelism, which makes great support for parallel processing, making it ideal for training deep learning models and running simulations. Optimization supported by most of the AI frameworks such as TensorFlow and PyTorch through optimized library like NVIDIA's CUDA. Okay, so these type of optimizations are available in GPUs, which are not available in CPUs. Scalability is there, easily scalable to multiple GPUs in order to handle huge AI workload. You can deploy more cores of GPUs to handle larger AI workload. But energy consumption is an issue here. Being power hungry in nature, GPUs exhibit increasing energy cost. Then cost is also the factor. High performance GPUs are usually quite costly with the cost multiplying in large deployment. So for large ML AI applications, the need of GPU or cost of GPU will be very high. So normally usage are training deep learning models, image and video processing, and running large scale simulations, etc. And if I go compare TPU, specifically designed for workload of artificial intelligence, particular for tensor operations used in deep learning. You have seen it earlier. Performance, this outperforms some performance benchmark by GPU. So some of the application will be running faster on TPUs. If this is deep learning application, will be running faster in TPUs compared to GPUs. And these are more power efficient than GPU for all type of AI workload. This is flexible, less versatile, flexibility less in TPUs because normally TPUs are designed for a particular specific ML applications or deep learning applications. So less versatile than GPUs. You want to run other applications on TPU, it's not possible normally or will become very slow. So these TPUs are specifically designed for deep learning applications. So it's less versatile compared to GPU. And accessibility is a problem. It's mainly available through Google Cloud, which may limit its use outside the environment. TensorFlow. The base use cases are TensorFlow based deep learning tasks, then large scale AI model training, and cloud based AI deployments. Next, which I discussed was FPGAs, which are basically programmable AI chips. So here customization can be done. They can be reprogrammed, providing a balance between good performance and flexibility in optimization for specific AI tasks. So you can program it for specific AI tasks and it will perform that task only until you reprogram it again. This is significant in that FPGA can offer reduced latency compared to CPU or GPU and therefore provide ideal for real-time AI applications. Because you don't need to go for fabrication. You take any suitable FPGA chip and program it for your particular application. It's very it's more energy efficient compared to CPU and GPUs because of their electronic technology or their fabrication technology. But some limitations are there. Programming complexity is there. Programming FPGAs for a specific task is not simple task. It's a very specialized task and specialized knowledge is required in programming and optimizing the optimizing the circuit. So that's why its use is very limited. Performance, though it is flexible, but performance of FPGA doesn't reach that of raw performance from GPU or TPU in large-scale AI tasks because FPGA are basically a general purpose chip which can be programmed for any general purpose application, image application, or AI application. So this is not designed specifically for AI application. That's why performance will be less compared to GPU or TPUs. But because we can program it if sufficient manpower or experts are available to program it, the programming and designing the particular function will be very fast compared to ASICs where we go for fabrication of particular AI/ML application and then after fabrication only that chip will be available for use. But here in FPGA, within hours you can program it and you can start working on that particular chip of FPGA. So used for real-time AI applications, low latency requirements, and specialized customizable AI tasks. Now, in turn, the base performance provided for specific tasks is they are built to be specific, application specific. Because you are designing this chip for particular specific application, so their performance will be better than this FPGA. Power efficiency is high. Cost of development is very high here because we have to go for fabrication. So ASICs are costly and take a lot of time in their development and they are recommended for high volume specific purpose application. You want to solve a problem and you want to run the application for long time for a particular ML application, then you can go for ASIC design or ASIC chip. So you will have to get it fabricated and then use it for in your server. So lack of flexibility, once designed, the ASIC cannot be reprogrammed, and hence they find application among only those target. So high volume specialized AI applications can run on ASICs. Edge computing with specific AI functions only can run on ASICs, and large scale data centers also are using ASIC chips. If we go towards your AI chips, that is better than TPUs. All AI applications are having three main components: the algorithm that forms the brain of AI model, the data that these algorithms learn from, that is training data, and finally the hardware that enables the algorithm to learn and run. So all these things can be packed into a single chip that will be called AI chip. So AI chips, the very heart of AI revolution, they are specifically designed processors that have been optimized to accelerate all operations related to AI, with particular focus on deep learning and machine learning. The complex mathematical operations, computations, and massively parallel computations involved in driving AI algorithm find an easy solution in these devices. So all AI chips feed on processing very large of amount data at a time. This parallel processing power for specialized hardware components greatly quickens all AI model training and inference, which in turn allows instantaneous response and opens opportunity for new applications as well. So if we are having a chip which is specifically designed for deep learning and machine learning applications, we can run a variety of applications on these chips. So those variety of applications will be having varying amount of training data and varying nature of the output required. So AI chips come with specialized processing units that are hardware units tailored explicitly for AI tasks such as neural network computation, matrix multiplication, and convolution operations, which are essential part of AI machine learning. When these units are compared to general purpose processor, we obtain large performance benefits because these crucial activities are accelerated significantly. So sometimes we call it AI accelerators also. For AI workload to meet fast data transmission, because if we are running some application on AI chips, then all neural network computation or deep learning computation will be there, which will be working on large amount of training data. So AI chip will be endowed with high bandwidth memory, we call it HBM, and effective memory access. So these high bandwidth memory are very fast in nature and though very costly. Making sure the processing units are receiving data constantly helps in invading bottlenecks and maximizing throughput. So if your processing unit is very fast, you are having thousands of multiplier units and accumulator units, but to populate those multiplier units and accumulator units, you are not feeding the data properly on with speed, then your application will become slow. So for this, we need a special kind of memory that is called HBM, high bandwidth memory. So AI chips are well suited to be developed in power constrained environments such as edge devices and mobile platform because they incorporate various techniques to reduce power consumption and hence heat dissipation. So this is a challenge here in designing AI chips, how to keep the power consumption minimum. Usually when we design memory like high bandwidth memory HBM power consumptions are very less, but to handle those HBM memories, we use multiplier units, accumulator units, means some process units are uh, uh, also fabricated on same chip. And all these processing units, like all thousands of multipliers, accumulators, and activation function calculators, they will be basically consuming the power. So heat dissipation is a big problem in designing these AI chips. So key architecture components in AI chips are basically tensor cores. Those are basically already found in GPUs. Tensor core excels at accelerating tensor operations like matrix multiplication and crucial for deep learning application. Then neural processing units, these specialized processors further refine the acceleration of neural network functions, making AI chip highly efficient for deep learning tasks. And we are having systolic arrays. The unique hardware arrangement provide additional performance boost for specific AI calculations. So AI chips have memory hierarchy that are optimized for AI workload, and these hierarchies help to minimize memory latency and ensure quick access to data as they are used frequently. AI workload demand rapid access to large amount of data. AI chip employ a multi-layered memory architecture, that is on-chip SRAMs, off-chip DRAMs, and high bandwidth memory. Combination of these three memories will be used to accelerate the neural network operations. So this memory will be having a multi-die architecture that are made up of multiple dies of silicons or chiplets, we call it chiplets, that are integrated together in a single package. Currently, the conventional chips, they are using only single layer of die and complete circuit is fabricated on that. So that we can say 2D chips. Only a square shape or die is there where we fabricate all the circuits on a single layer or single wafer. But this will be a multi-die architecture, one above another. This is 3D structure. So multiple dies layer will be there, and on each layer, memory will be constructed. And then out of those multiple layers, we create memory banks, etc. So these AI chips are usually called neuromorphic chips, and they mimic the structure of and functions of biological neural network. This aims to provide more efficient AI processing. And in recent development, Intel and IBMs are into the development of neuromorphic chips, including Intel's Lohi, and that push the boundaries of what can be done with AI, specifically in terms of power efficiency and real-time processing. So these neural processing units, NPUs, specifically optimized for neural network and performs much better than CPU and GPUs. So any neural network, as you are aware, will be having some one new input layer, some multiple hidden layers, and some output layer. And for each input, for each layer, output is going to all the neurons of next layer. And then with each connection, we are having associated weight also that will be trained during the training of this model. So this is a simple artificial neural network. Let's see how this network is basically converted to a particular AI chip architecture. So we are having neurons, we are having weights, we are having connections between neurons, and with each connection, we are having associated weights. Like when we feed input data, suppose input 5 neurons are there, then these neurons are connected to next layer near neurons. So all the input neurons are connected to a particular neuron of each neuron of next layer. So if 5 inputs are there, 5 inputs will be to this next hidden layer node. So these 5 inputs are going to each node of next layer. So with each input, with each input going to particular neuron, we are having associated weight in neural network. So this input and weight will be multiplied. So we are having a vector of input, we are having a vector of weights, and all these two vectors, or we can call it matrix also. These two matrices will be multiplied, and some output will be generated. These output will be added together to generate a single value sum, and this sum will be fed to some activation function that will be generating output for that particular neuron. So this is normally architecture of your deep learning model or neural network model. Like I give one example, like we have trained a neural network to classify some images of some creatures. So like if dog is there, then suppose four different creatures are there, then four outputs will be there in this neural network, some hidden layers and some input layers. So when we feed dog image into this input, one particular output of this network or this deep learning model will go 1. Remaining outputs will be 0. So that indicates we have identified this image as dog, or we have classified this image as dog. Similarly, for other image like cat, second output will be high. For bird, third output will be high and remaining output will be 0. And for fish, fourth output will be 1 and remaining will be 0. So to perform this training and computation and inference, we need some AI chip. That is a combination of GPU plus high bandwidth memory. So this GPU is connected with multiple HBMs throughout, and these HBM will be supplying the data and weights corresponding to particular layer. So large amount of training data will be stored in these HBMs, and there will be arrangement to supply this data efficiently to GPU so that GPU doesn't wait for next input. So this is normally processing some many multiplications we have to do in parallel. Then for parallel sum, we can use this hierarchical structure so that two multiplication results are combined using one adder, then next two multiplication results are combined using another adder, and then result of these two adders are combined by further adders, and so on. And finally, in few steps, we can make the summation ready or this accumulation ready. And this final result will be used for activation function input. So normal common type of memory are basically DDR, which are very popular, and low power DDRs are there. Then GDDRs are there, that is graphics double data rate memory, and we are having HBMs. So very high bandwidth and density is provided by these HBMs. This is a typical architecture of high bandwidth memory. We are having, as I said, multiple layers of silicons are there. Each layer is having large amount of storage available, and these layers are separated by some other material. And below that, we are having silicon interposer and PCB substrate. That this PCB substrate will be connecting this complete computation result to your GPUs. And we are having an inbuilt processor here, either CPU or GPU, that will be uh, basically using the data stored in this HBM for their matrix multiplication computation, addition, accumulation, and activation function computation. So HBM stacks DRAM dies vertically on top of a base logic die. We are having interconnection between these dies called TSVs, and we are having micro bumps which are separating two layers. Then we are having substrates. The stack is oftenly the complete DRAM stack is oftenly connected to a CPU or GPU through a substrate like silicon interposer. So the complete data transfer between your CPU or GPU and HBM will be done through this interposer. Then we are having interface so that this interface will be supplying the data from HBM directly to GPU or CPU. So this is another diagram, like we are having connections between different layers of DRAM. Then we are having a logic die, that is the physical die, which are connected with all these four layers of memory. and this logic die will be having connection with CPU, GPU or other things which are making the computation, matrix computation and accumulation and activation function calculation. And finally, this is done through interposer, that is interaction between GPU and all HBM dies will be done through interposer. And this interposer having connection with package substrate also, that will be because we are having other GPUs also which are doing other tasks of machine learning. So final result of this computation will be passing through this package substrate to other GPUs. So bandwidth, HBM can achieve bandwidth higher than 256 gigabytes per second. Power consumption will be less than DDR4 or GDDR5. Form factor HBM is smaller than DDR4 or DDR5 because we are having multiple layers of substrate here or the silicon wafers. But some challenges are still there with HBM. They are very expensive because memory is very fast. Associated hardware is also required. Multiple layers you need to fix into one chip. So it's a very expensive task. HBM is difficult to scale, like you want to double the memory size, you cannot connect two HBMs and make the memory size double, or you cannot connect four HBMs, or you cannot connect 16 HBMs to create a larger memory. So scalability is an issue here. So when we design a particular AI chip, we go for a particular size of HBM, and that size will be fixed, and running application will have to deal with that size only. And integration of HBM with existing system is difficult because this is specifically designed for AI chips and GPUs. So integration of this HBM is difficult with normal general purpose CPUs. So these are various forms of HBM or various generation of HBM. Started in 2016, HBM2 came where bandwidth was 256 gigabytes per second, and IO speed was 2 gigabits per second because we are transferring data in parallel. So total bandwidth is 256 GB per second. Then in 18, the bandwidth increased to 460 GB per second. In HBM3 2021, this bandwidth increased to 665, greater than 665 gigabytes per second. And next generation of HBM3 is going up to 1075 gigabytes per second. And IO speed has increased for single transfer to 8.4 gigabytes per second. So this is typical architecture of HBM memory unit. Then if I go to key performance factors of HBM, so bandwidth is above is reaching around or crossing around 1000 gigabytes per second. Power is normally very less. We are having 8 channel HBM, 16 channel HBM, and currently fabrication is going on for 64 channel HBMs. And these HBM stack is basically divided into several banks and bank groups so that you can use a particular bank for particular size application of your deep learning application. There are some issues or challenges related to HBM. One is the heat, another is capacity, and third is the cost. So normally memory is not generating not that amount of heat, but associated processor which you fabricate on same HBM chip is basically problem because that processor will be just controlling the data access from this HBM stack. So that processor will be generating a great amount of heat. So that is a problem currently. HBM capacity is very limited compared to DRAM. While HBM gaining in capacity, it can never catch up the external memory because external memory is capable of utilizing every enhancement made within the package as well. HBM requires an interposer or bridge, and this is still relatively new technology. an interposer requires the fabrication of what is basically a PCB in silicon, and that will be basically costly affair because interposer will be similar to a general purpose computer which will be controlling the HBM units. So fabrication of this is a costly affair, and also heat will be generated by this circuit. Real life implementation of neural processing units are basically TPUs provided by Google. Then we have NNP, Myred, IQ by Intel. These three technologies are by Intel. Then NVDLA by NVIDIA, AWS Inferentia by Amazon, Ali NPU by Alibaba, and many others are listed here. So these are the companies, they are working on fabrication of NPUs, and they are continuously updating this technology, updating the technology of HBM, updating the technology of multiplier units, accumulator units, and activation units, etc., and making it faster and faster. So if I conclude, HBM delivers considerably more bandwidth than any previous memory system at a power per bit level that could be an order of magnitude better than external DDR memory systems. So power consumption is better in compared to DDR memory system. If we connect external DDR memory system, power is better. It also will enable a significant increase in total compute throughput, but this will come at expense of total power in both memory subsystem and from compute. Keeping these systems fed with enough power and cool enough to ensure a safe operating environment for the DRAM memory may become a challenge. And thank you. That's all from my side.
Thank you, sir. Thank you for such an insightful talk. If anyone have any questions,
And this can
look,
be a research topic also. If you are working, if some of you are wants to work on hardware fabrication, etc. So this HBM technology, AI chip technology, and TPUs can be a future research area also.
yes, sir. As a programmer, we should always understand the underlying architecture and hardware limitations. Only that will help us to design better architecture in terms of large scale deployment. Thank you, sir. Thank you for the talk.